Hi, today I'm going to be going over the first problem of exam 2 for EML 3100. We're given a thermodynamic system consisting of a co-flowing heat exchanger where one stream is oxygen and the other stream is nitrogen. And by co-flowing, the problem is telling us that both streams are moving in the same direction. And a heat exchanger's function is for two or more fluids to thermally interact, which I've signified by this green arrow here. So the blue side up here, we have oxygen flowing from left to right, and on the bottom side, the red side, we've got nitrogen flowing from left to right. To make an initial assumption that the only energetic interaction is between the two streams, I've drawn in dashed black around the entire heat exchanger just a schematic of some thermal insulation so that we aren't accounting for any interactions between our system and the environment outside. Similarly for the outlet pipes and the inlet pipes, we don't assume any heat transfer is taking place. What's given in the problem statement, in addition to the configuration, are the inlet conditions. On the oxygen side, we've got a temperature of minus 17 degrees centigrade, a pressure of 200 kPa, and a mass flow rate of 0.25 kilograms per second. On the nitrogen side, we have a temperature of 500 Kelvin, a pressure of 150 kPa, and a mass flow rate of 0.6 kg per second. Additionally, the problem statement tells us that the heat exchanger is efficient enough to allow these fluids to essentially reach thermal equilibrium at the outlet. And this can be translated into an equation, essentially. If I move over here, none of the outlet conditions are given for the heat exchanger, and obviously we need to do some analysis to figure out what's happening at the outlet in terms of our thermodynamic conditions. But this thermal equilibrium constraint helps us out a little bit by eliminating one of the unknowns. We can assume that T2, the outlet temperature of the oxygen system, and T4, the outlet temperature of the nitrogen system, are equivalent to each other. They've reached thermal equilibrium, and we can combine those into one variable, which I've boxed over here, this statement, and I've called it T out. And this is ultimately what the problem is asking us to find. So our analysis needs to lead us in a direction where we can isolate this variable and calculate it in terms of other given information. Last but not least, in terms of givens, we're given the heat capacities at constant pressure for both substances. For oxygen, it's listed as 0.922 kilojoules per kilogram Kelvin, and for the nitrogen side, we've got 1.042 kilojoules per kilogram Kelvin. It also tells us that during the analysis, we can assume both of these heat capacities to be constant and neglect any temperature or other dependence they may have. I want to emphasize the fact that I've drawn 3 total control volumes. We've got one surrounding the entire heat exchanger that crosses through both the outlet pipes and both of the inlet pipes. But also I've drawn an interface in between, which breaks this into 2 smaller control volumes, so that if I choose to do a particular analysis on either side, I can isolate them. One of the consequences of the energetic assumption I made regarding the heat transfer earlier on is that the only interaction occurs between this interface in between, this thermal interface. Again, no mass transfer, but only heat transfer. So that when I say isolate this bottom control volume, I should really only have 3 interactions. I should have a flow coming in to this bottom control volume, and the flow carries energy with it. There should be some heat transfer due to the thermal interaction across this interface, and then also there's a flow out of this control volume, which also carries energy with it. So these are the only things that we really need to keep track of when we say apply the first law. The same type of thought process can be considered applicable to the top control volume. And for the larger control volume, you see that there is no energetic interaction. Everything takes place inside. So if we were to apply, say, mass conservation to this control volume, we would have to deal with 4 streams, but energy conservation wouldn't really give us much. Before proceeding further with the analysis, we need to determine where we lie on a thermodynamic diagram, given the inlet conditions for both oxygen and nitrogen. What phase are both of these fluids in? What I've drawn for each gas, that's what I'm assuming right now based on just an initial pass of these numbers, are PT plots or phase diagrams. And I've just given a very, very basic sketch of what the saturation curve looks like, say the critical point up here and the triple point down here for each substance. And looking at the oxygen side, I've just said let's take the pressure at 200 kPa and find out what the corresponding saturation temperature is. And if we look in the tables in the back of the book, you'll find that the corresponding saturation temperature is approximately 90 Kelvin. It's pretty cold, cryogenic. But if we look at where we actually lie, so minus 17 degrees centigrade, if we add 273 to it, we can convert from centigrade to Kelvin, we get 256 Kelvin. And because the actual temperature is much, much greater than the saturation temperature for the given pressure in the problem, we can assume and actually find that our oxygen in the heat exchanger is a highly superheated vapor. And because it's so superheated and lies way out here on the PT diagram, it's actually a good assumption that we're operating with an ideal gas on the oxygen side. And we find essentially the same thing on the nitrogen side. If we look at the pressure, 150 kPa, given the problem statement, and find its corresponding saturation temperature in the tables, we get 80 Kelvin, a little bit less than the oxygen. But we're operating at 500 Kelvin. So again, we've got a highly superheated vapor. And in this case, because we're operating at relatively low pressures and high temperatures, and both gases exist in the superheated vapor state, assuming that they behave as ideal gases is not a bad assumption. To recap on all of the assumptions we've made up to this point, I've listed them out. First and foremost, both the heat exchanger and the supply lines are perfectly insulated, so no erroneous heat transfer into the system. The inner compartment of the heat exchanger, both of them are in perfect thermal contact with each other, and that is the only energetic interaction in this problem. Third, both of the fluids are to be analyzed as ideal gases, and this was shown using the saturation curves in the PT plots shown in the previous slide. And finally, because we're analyzing the fluids as ideal gases, and I've listed on the side over here, you should remember or recall that both the internal energy and the enthalpy are functions of temperature only, and the pressure does not play a role if we conduct an ideal gas analysis. So the pressure information given in the problem is actually superfluous. It's just additional excess information to trip you up. If it was necessary, a good assumption to make, though, would be that there's negligible pressure loss across the heat exchanger because only information was given on the upstream side, nothing on the downstream side. So for problems where only upstream pressure information is given and say a process is not specified, it's a decent assumption to say that the pressure loss across the system is negligible. So P2 per se would be equal to P1 and P4 equal to P3. Continuing on with the analysis, we'll first apply the conservation of mass continuity, okay, for each of the sub-control volumes that I defined previously. So on the oxygen side and the nitrogen side, we will assume, in addition to the previous assumptions, that both flows are in a steady state situation. And this just means that the heat exchanger isn't undergoing a startup transient or shutdown transient, and things have been fully developed through the system and aren't really changing from point to point in time. So conservation of mass reduces to the following with this assumption. Really just the mass flow rate into the system, the oxygen system at 1 is equal to the mass flow rate out of the system at 2. And because they're equivalent, we can combine them into one variable that I'm going to define as m dot O2. Very similar on the nitrogen side, m dot 3 is equal to m dot 4. And I'm going to combine these into one variable, m dot N2. Moving on now to energy conservation, or the first law of thermodynamics. We're also going to assume a steady state situation. And the first law reduces to the following. For the oxygen system, we have an enthalpy flux on the inlet side, so m dot 1 H1. Again, we're using enthalpy for both systems because it's an open loop control volume problem, and we have to account for the pressure work or the boundary work on the upstream and downstream sides. That's why we're using H instead of U. So again, we have m dot 1 H1 plus Q dot, the energy from the thermal interaction from the nitrogen side coming into the system. That's why the plus sign is here. And again, just refer back to the control volume if you're having trouble with the signs. There is no real convention. You could choose the direction to be either way. You just need to be consistent when you break your problem down into smaller control volumes. And then on the outlet side, we have m dot 2 H2. And similarly, on the nitrogen side, we have m dot 3 on the inlet side. We're removing the same amount of energy, so the same variable Q dot minus Q dot, and this is equal to the enthalpy flux on the outlet side, m dot 4 H4. If we go ahead and combine the expressions or the equations that we derived in both Part A, mass conservation, and Part B, energy conservation, we can actually come up with a global expression for the outlet temperature. So what we're doing is essentially, again, like I said, combining what we did in Part A and B. We're going to solve for the Q because it was the same variable in between both the equations, and then equate the resulting expressions and solve for the outlet temperature, which is going to be the only unknown left to solve for and what was asked for in the problem statement. Again, just some side notes. Over here, because we have an ideal gas, we're assuming that the enthalpy only has a temperature dependence, not a pressure dependence. Again, the erroneous information that was given in the problem statement on both the inlet streams. So essentially, we can break up our dT dependence, or dH dependence, using Cp dt, integrate that to get delta expressions, and that's how I was relating Cp to temperature using the expressions in Part B of the analysis. Again, here are the mass flow rates, equivalent on the inlet side equal to MO2, and equivalent on the nitrogen side equal to MN2. And then the constraint from the problem statement that at the exit of the heat exchanger we have a thermal equilibrium, T2 equals to T4. And using all of this information, again, all of our assumptions, and combining the expressions from A and B, we get this expression down here at the bottom for T out, the outlet temperature of the heat exchanger, which is the same temperature on both streams. So the T out is equal to T2 is equal to T4. And what you see is that it's nothing more than a weighted average between T3 and T1. T3 being the inlet temperature on the nitrogen side, and T1 being the inlet temperature on the oxygen side. And the weighting factors are as follows. On the nitrogen side, we've got the thermal capacity of the nitrogen side, or m dot N2 times Cp N2, divided by the total thermal capacity of the combined oxygen-nitrogen system, m dot N2 Cp N2 plus m dot O2 Cp O2. And it's the same denominator on the oxygen side, but we've got the thermal capacity of the oxygen system, m dot O2 CpO2, on the numerator, and that's what's weighting. This whole expression is weighting the inlet temperature on the oxygen side. And it's worth noting, if you look at the units, once we combine these two or multiply them together, we've got kilograms per second times kilojoules per kilogram Kelvin, and the resulting unit is kilowatts per Kelvin. And because we have an open flow system, and we're dealing with heating rates, what this really tells us, this is the thermal capacity in terms of the heating rate necessary to raise the temperature by 1 Kelvin, okay? And once you plug in the numbers, you'll see that the nitrogen side actually has a bit higher capacity than the oxygen side due to the fact that it's got higher flow rate and a higher specific heat capacity. The result to the outlet temperature is 434 Kelvin, or approximately. And just as a sanity check, this falls in between the 500 Kelvin on the nitrogen side and the 256 Kelvin on the oxygen side. It would be a violation of the second law of thermodynamics, which has not been covered yet, for the temperature to be out of that range. So 430 Kelvin sounds just about right.
The Teaching Center, UF's Learning Resource Center.